Okay, let's continue our okay, our next lecture we will discuss about how to build the code, the neural network from scratch. Okay, we try to build the artificial neural network code from scratch. So before I explained this code, okay, let me go back to the slide where we have the general step or the general algorithm to the one that we want to implement in Matlab, which is yep, this one. Okay, so as you can see here that before we start build this code, we try to make sure that every variables that involved in our network from forward pass to the backward pass is converted into a matrix here. But of course in this matrix or in vector version here, it's actually explained detail about, you can see there is detail about the backward pass, but for forward pass we don't have explained that details in details, but that's why we need to I need to make sure that you have a clear information. Actually this is also need this operation, which is step number 2 here, is a forward pass where you need to also convert everything in vector version, so it's easy for you to do the calculation. So again, as you can see that like this one, okay, this one is we try to only show we show you only how actually we convert the matrix of the hidden layer, the wake, okay, the wake that involved at the hidden layer. We try to convert all the W into a matrix where this is represented by this a capital W here, which is represent all the matrix involved at the hidden layer. Then okay, so okay, so if you can see in this diagram, okay, that's mean actually everything can be converted into matrix forms. Okay, for example, again I think this one we already discussed that we can represent all this wake by one vector which represent the matrix there. So meaning that you have a capital W of your hidden layer, which is equal to your W11. So you can see that this numbering here, okay, or this number here represent the coordinate or the index inside the matrix. So that's why you need to arrange appropriately according to this this number. Okay, so means that this one is row number 1, column number 1, row number 2, column number 2. So this one should be W21, and then this is W12, W22. Okay, so means that everything there is a W at this second layer. Okay, same goes to the W at the wake involved at the output layer. You need to arrange in matrix forms or in vector. So it should be equal W11, W21, W12, and W22, which is the W at the layer number 3 or the output layer. Okay, So again, same goes to the bias. So the bias, okay, like this one, you need to have the matrix, a bold matrix, which is, it should be bold matrix B, B2, which is equal to your B1 2 and B2 2. So the matrix itself, you can see that it's the position is arranged according to the arrangements there. You can see, because this one is at the upper, this is at the lower, that's why we have 2 times 1 matrix like this. Means that if let's say you have more than 2 neuron at the hidden layer, 1 2 3 for example, there's another neuron here, 3, and again you will have 3 bias at this layer. So then you need to have the B should be arranged in that way, B1 B2 and B3. Okay, so that is the easiest way to do, because if I cannot, I don't want to make it more complicated. That's why we arrange it in the same way how we arrange the bias position at the ANN architecture here. The same we arrange in the metric form there, the elements. Means that the elements there, if this is B1, this is B2, then you have 2 times 1 matrix. Okay, so same goes to the bias at the output layer. So you need to arrange in the same forms there. So B of your output layer should be equal to B1 B2 2 2. Okay, so because we try to arrange it in the version of we arrange it in vertically. The matrix is vertically arranged like this one, is because of we want to have a number which is similar position as the architecture inside this one. Okay, because this one is seem to be vertically arranged, so that's why in the matrix also we do the same. So then it will not confuse you when you try to compute anything there. Okay, so same goes to the inputs there, x1 and x2. Okay, you can just put it as x, which is equal to you must arrange in this way, x1 x2. Okay, so later I will show you that in my Matlab codes. Okay, the arrangement of x1 x is actually in this way. So that's why during when we compute the algorithm, we need to convert this x into x transpose. So then you will have x1 and x2 in that position. Okay, because we want to have the same format, which is in vertical patterns there. So then it will be easy for us to do some computation. So means that for example, if we want to convert, if we want to find net, okay, net is equal to, let's say net 2 is equal to our W, okay, our W2 multiply with our x there, x plus b. So this one is this matrix, this one is in this version, and this one is in this version. Okay, so then you will obtain the net there is net 2. Means that when I said net 2 means that is a metric version where it consists of net 1, which is at the layer 2, and net 2 at the layer 2. So you will get the matrix there, where these variables hold both net 1 and net 2 at the second layer. So that's how we do codings there. Easy for us to do in Matlab, because Matlab is a metric based programming. So everything's we do should be in matrix. So then it's easy for us to speed up the coding, because everything should be done in matrix, so you don't have to do a many for loop just to compute each and every variables, because once you combine all this the same variable into one matrix, then it's easy for you to compute parallelly by using the Matlab's code there. Okay. Let's go back to this code there. Okay, what you need to know, that there's three main codes there. One is backpropagation.m, and then you has a sigmoid functions.m, and then the main function is this one, simple ANN.m. Okay, so that means that this is the main function, where at this function we will call this function backpropagation and sigmoid. Okay, sigmoid and backpropagation is a sub function that you will call at this main function. Okay, let's discuss about, okay, this is sigmoid is nothing, it's just a definition of your activation function. We try to okay, this is the function. Okay, this is of course this is a sigmoid function, means that the input is the net. Again, the input is the net, and then the output is the O there, represent the O in your ANN. So okay, in your ANN, and then we have a back propagation here. Okay, at the back propagation, the input we have 1, 2, 3, 4, 5, 6. You have a 6 argument. Okay, 6 input. So W2 is for your the wake involved at the hidden layer. Okay, again, if you go back here, okay, this is your W2, means that this one it means it's this one, it's a metric form, it's not only one W. The W2 represent all W involved at the layer number 2, and then the W3 is the matrix that will hold all value of W that involved in layer number 3, and then same go to B2 and B3. Okay, B2 will hold the bias at the layer number 2, and then B3 will hold all the bias happen at the layer number 3. So you will have W2, W3, B2, B3, and this X and Y is the training data, means that you will have training data, the input X and the actual output Y, which is also in matrix form. Means that if you have a lot of input, then you just put it in matrix form. X1, X2, and X3 must inside that capital X. Okay, so and then inside this function we already set our alpha that is 0.9. This is just an example. So we just you can set anything, any point that you want. It's still but this one, because we want to show that this algorithm works, so you can set any numbers that you want. And then okay, n here is a number of iteration. Okay, why is n equal to 4? Because at this example you only have a 4 training data set. I'm sorry, you have a 4 sample inside your training data set. Okay, you will have at the simple ANN there, you have only 4 sample inside your training data set. So that's why you set that in equal to 4. Means that let's say you have 100 sample inside your data set, then you need to set n equal to 100. It's a number of iteration. Okay, just a number of iteration. So this for loop is represent 1 iteration. So again, as you can see that okay, so let's say you go to iteration number 1, k equal to 1. Okay, once a k equal to 1, then you will do the back pass, feed the samples, and then you feed the sample, and then you doing the forward pass algorithm. So before I go deep into explain this one, let's discuss about the main function first, because if you don't familiar with the input, or you don't familiar with your training data, if I don't explain this, the characteristic of this training data, then you not sure what happened here. Okay, so let's go here. Okay, this is my training data, which is consists of x and y. X is the input, y is the actual output. But again, if you remember that we convert the output into one hot format. Actually, this is a simple data set. Actually, if you refer to any text, any AI textbook or any machine learning textbook, they call this one as a exclusive OR operation. Of course, this is exclusive OR. So how you know that this is a exclusive OR? Okay. Yes. Okay. So it's an exclusive OR because your x there. Okay, this is your x, this is your y, and then when you have a 0 0, then it should be here should be what? 0 0 1. That is exclusive OR operation, right? 0 1 you will have 1, and then 1 0 you will have 1, and then 1 1 you will have 0. Means that it's a exclusive OR operation. This is your x1, this is your x2, and this is your y. Okay, but of course this is the best way to try to show that our algorithms works. I try to implement the neural network which behave like exclusive OR. Of course, exclusive OR is not challenging as compared to a real application, but I just want to show you that the ANN itself is work. Means that of course in practical or in real application, you will not using the artificial neural network to solve exclusive OR, because you just simply use the exclusive OR gate. You can try to solve this problem easily as compared to try to train the data by using neural network, and then that neural network work as a exclusive OR. But this one just to make sure that you just want to prove to you that our algorithm is work. Okay, so that's why this is the original data set. Okay, original data set. What we do is just we convert the output into one hot version, which is y1 y2. Okay, this is y1 and y2. Then you will have 0 0 you put as a 1 1 0, and then anything which is 1 you put as a 1 0 1 0 1. Okay, if the output is 0, then you put as 1 0. So just convert it into one hot format. So that's why you see in this coding here, the x is still there, but the output is in this format. So now again, why we need to use the output? You have 2 there, because remember that our architectures there, you will have 2 output there. This one is y1, this is y2. Okay, okay. After that, then you need to do it. If you remember that in our slide there, okay, the first step is you need to initialize the wake with adequate value. when I said initialize the wakes, that is also include with the bias. You must initialize the wake and the bias with the adequate value. But in real way to in real application, how to do this is just by set the W and B with the random number. Okay, that is one way. You can initialize with the random number. So that's why you see in this code there's a random number. I just generate a 2 times 2 matrix, the random number where the size of the random number is 2 times 2. Same goes to the bias. So why this is 2 times 2, this is 2 times 2, and this one is 2 times 1, this is 2 times 1. So at this one, okay, why once you implement this this code, so the W2 is equal to, you will generate a 2 times 2 matrix where this is random number, this is random number, this is random number, and this is random number. So same goes to W3. Okay, random number, random number, random number, and random number. And then you also generate B2. B2, you will generate only 2 random number, one here and one here, because you set it 2 times 1 matrix. This one is 2 times 1, this is 2 times 2. So as you can see that this format is similar to the one that I explained before, which is this part. So you can see that W2 you must have 2 times 2 matrix, W3 you have 2 times 2 matrix, and B2 and B3 you have 2 times 1 matrix. And during the initialization you just set with a random number. So that is that initialization is represented by this code. Okay, and then once you have the initialization process, the next step is you will call the backpropagation function. Okay, which is this one. Okay, as you can see that each time you call backpropagation function, since this is a stochastic gradient descent again, that's why you can see that at the end of this code, the W will be updated, which is this one, and this W is updated, this W2 is updated, W3 is updated, and the bias is also updated. This one B2, this one is B2, this one is B3. Okay, and then so that's mean once you call back propagation function, that is actually you will do the iteration here. Now the iteration is equal to 4 because our number, the numbers of sample inside our data set is 4 only. You have 1, 2, 3, 4. So that's why this loop will do iteration number 1, iteration number 2, iteration number 3, iteration number 4. Okay, each time you do the iteration, you will update all the W and B. Means that when you call the back propagation function, you will update 4 times because of this loop is repeated 4 times. And then you can see the main functions there. Once you finish one time, it will repeat it. That is only represent one epoch only. So these things will be repeated 10,000 times because of you set the maximum epoch is 10,000. It will repeated this activity 10,000 times or 10,000 epoch, and each time one epoch you will call this back propagation function, and this back propagation function will repeat 4 times, 4 iteration, and each iteration will update the W. Means that one epoch you will update the W 4 times. Okay, okay, let's go to the back propagation function. Okay, iteration number 1, k equal to 1. First you need to fit the data. Of course, because your data set there, the capital X represent the whole data set, and Y, capital Y, represent the whole data set, the whole samples. And then of course at this process you need to call one by one, so that's why you can see that when k equal to 2, I just call when k equal to 2, k equal to 1, then I just call the first data, which is this one, of course this one. Okay, I just call that data. Means that your at this code here, the small x there is equal to what? We'll get 0 0. Okay, then your the small y there, you will obtain the 1 0. But you can see that I put the apostrophe there. This one is to make sure that it will transpose, because remember that because our architecture there, we want to have everything in vertical because the architecture seem to be a vertical that everything is positioning in vertical way. So that's why actually it should be 1 0 apostrophe 0 0 apostrophe, or is equal to 0 0, and this one should be equal to 1 0. Okay, so why we do this is because of we want to make sure that the architecture is the numbers there, elements there, is similar to our architecture here. Means that the input should be in this verticals oriented, and the output also is in vertical oriented.